All right, so finishing up with chapter 6, there's really just two things to talk about. And they both piggyback off of the concept of specific heat that we brought up in Monday's lecture. Now, with regard to specific heat, we're looking at one equation in particular. We're looking at the equation of Q is equal to MC delta T. The heat of the reaction is equal to the mass times its specific heat times its change in temperature. And so with that information, we can answer questions like this. How much heat needs to be added to 15 grams of water to raise its temperature from 25 to 75 degrees Celsius? So the specific heat value, the value of C, is going to get drawn from a table of values. Water in the liquid phase has a specific heat of 4.184 joules per gram degrees Celsius. So I've got a mass of 15.0 grams. I've got a specific heat of 4.184 joules per gram degrees Celsius. And my delta T, my change in temperature, is final temperature minus initial temperature. My initial temperature was 25 degrees. My final temperature is 75. 75.0 minus 25.0 will give me 50.0 degrees Celsius. So all told, I put those values in, 15.0 grams multiplied by 4.184 joules per gram degrees Celsius multiplied by 50.0 degrees Celsius. What I can see, my grams cancel, my degrees Celsius is canceled. I'm left with just joules. 15.0 times 4.184 times 50 gives me to three significant figures because I have 3 in the mass and 3 in the temperature. 3,140 joules of energy. Now, one thing to pay attention to is if you did your change in temperature incorrectly, let's say that you flipped the 25 and the 75, and you got a negative 50 value there, you'd still have gotten the same value. You'd have still got 3,140 joules. It would have just come out as negative 3,140 joules because of the negative change in temperature. In these calculations, the sign is just an indication of the direction that the heat is going. When the heat is leaving the system, we're going to see a negative sign on that value of Q. When the heat is entering the system, we're going to see a positive value on that Q. Any questions about this example? Now, this secondary question here asks us essentially the reverse of the process. So let's just take off this part here. If the heat changes when the water goes back down from 75 to 25, the only thing that is changing there is my delta T. My delta T, we're now going from 25.0 degrees is where we end. 75.0 degrees is where we started. My delta T in this case would be negative 50.0 degrees, which if this Q value was 3,140 joules in the positive direction, since the only thing that changed is that this positive 50 turns into a negative 50, the only thing that'll change here is that this will be a negative 3,140 joules. Again, here's where we show that sign convention. In the first example, heat went into the water and raised its temperature. That's why the sign was positive. In this case, heat is leaving the water, lowering its temperature, and that's why we get this negative. So positive and negative are just functions of the direction that the heat is going. Is it going into the system and raising its temperature, or is it flowing out of the system and lowering its temperature? All right, let's look at another one. The specific heat of aluminum is 0.895 joules per gram degree Celsius. If 156 grams of aluminum at 75.5 or 75.0 degrees Celsius is cooled to 25.5 degrees Celsius, how much heat is transferred? And what is the sign of Q and what is its significance? Well, we've got all the values that we need. Here's my specific heat. Here's my mass. For delta T, my final temperature is 25.5 degrees Celsius. My initial temperature is 75.0 degrees Celsius. If I subtract those two from each other, I get negative 49.5 degrees Celsius. Since my sign of delta T also determines my sign of Q, I know that the temperature of the aluminum is going down, which means that the heat is leaving the aluminum. How much heat? Well, that's where my calculation comes in. 156 grams multiplied by 0.895 joules per gram degree Celsius multiplied by negative 49.5 degrees Celsius. I get a Q value, 156 times 0.895 times negative 49.5 to three significant figures again. I have 3 in my mass, 3 in my temperature, and 3 in my specific heat. Negative 6,910 joules is my correct answer. So how much heat is transferred? 6,910 joules. What is the sign of Q? It's negative. What does that mean? It means that the heat is going out of the aluminum. And as the heat leaves the aluminum, it drops the temperature of the aluminum. All right, any questions with regard to this one? All right, this is our last question regarding specific heat. Then we're going to talk about one other concept related to heat transfer. If a kilojoule of heat is added to each of these substances, each of them in 50-gram quantities, what would increase by the greatest amount in terms of temperature? Would it be aluminum, copper, or lead? So think about this for a second. If you're watching on Zoom, go ahead, put an answer into the chat. You do not need to calculate this, although you could. You should be able to logic your way through it. So which one of these is going to increase in temperature by the most? You're saying aluminum as well? All right, we're getting a lot of aluminums. Anyone willing to disagree? Okay, those of you that are choosing aluminum, I'm assuming it's based on the fact that the specific heat is the greatest. And that would actually be the reverse logic of what we need. We can do this calculation really quickly. A kilojoule of energy is 1,000 joules. If I divide it by the 50 grams and the specific heat, that would give me my change in temperature. So real quick, 1,000 divided by 50 divided by 0.895. The aluminum would change by 22.3 degrees. The copper would actually change by 53.1 degrees. And the lead would change by 155 degrees. You have to consider what specific heat means. Specific heat is the amount of energy that it takes to cause the temperature to change. A lower specific heat means that less heat is required to change the temperature. So if I'm giving all of them the same amount of energy, the one that has the lowest specific heat is going to increase the most because it requires the least amount of energy to change. Adria, question?
Well, I was going to guess lead because it has the greatest mass.
Okay, that actually doesn't have as much to do with it as you think. It really does come down to specific heat. There's really not a trend that exists that relates molar mass and specific heat to each other. So how did I get these numbers? So keeping in mind our equation, Q is equal to MC delta T. If I'm trying to isolate delta T, I'm going to divide each side by M and C. So Q over MC is equal to delta T. The Q is my 1,000 joules. My M is my 50 degrees. And then my C value is whatever the specific heat was. So for the aluminum, I took 1,000 divided by 50, divided by 0.895, and that gave me the 22.3 degrees Celsius. Any other questions here? Okay, so the last thing that we want to talk about here is something called calorimetry. Now, we're not going to spend a whole lot of time talking about calorimetry. It can get real complicated real quick for us. But what we can do is we can speak to kind of the general idea of what calorimetry is and what it's used for. In general, calorimetry is a technique that we use to determine changes of heat as a result of chemical and physical reactions. It's done in an instrument called a calorimeter. Calorimeter is basically an insulated cup of sorts. You can make a real cheap and easy one using a couple of coffee cups that are just nested together and then put a lid on. And what this allows us to do is, according to the law of conservation, we know that the heat change for the system and the heat change of surroundings together have to be zero. That's the law of conservation of energy. Whatever heat is generated by the chemical reaction has to be absorbed by the surroundings, and vice versa. So what this allows you to do is, if you can measure the heat of the water, which is part of the surroundings, that will actually be opposite of the heat of the reaction. So I figure out what's going on in the water increases in temperature. We can calculate how much heat it absorbs. And then we can say, okay, well, then that must have come from the reaction that occurred inside the water. And we don't need to get into all of these calculations here. All that we really can get into. So if we followed along with this, we would have 100 grams of water undergoing a temperature change. We could do a heat calculation on the water. 100 grams of water times 4.184 joules per gram degrees Celsius, its specific heat. Temperature change, the difference here would be 4.45 degrees Celsius. And so if I did that calculation, 100 times 4.184 times 4.45 to 3 significant figures because of my temperature, I get that the water gained 1,860 joules of energy. And since the heat of the water would be the opposite of the heat of the copper pipe, if this is positive 1,860 joules, then the heat of the copper pipe would be negative 1,860 joules. Why negative? Well, the water gaining heat, increasing in temperature, that energy had to come from somewhere. Where did that energy come from? It came from the hot pipe that was dropped into the water before the reaction started. So this isn't actually a chemical change, this is a physical one. But we can monitor how much heat was transferred in that kind of way. And that's really what calorimetry is for. Where we see calorimetry used the most often is a version of this is used for determining how many calories are in food. Using calorimetry, you can essentially take a food sample and burn it and use the heat from the combustion of that food sample burning and figure out how much it changes the temperature of the water around it to figure out how much energy is in that food. Now, we call food energy calories, and that's what largely drives our nutrition facts to determine, okay, you know, this bag of Cheetos has 130 calories per serving. Well, how did I figure that out? Well, a calorimeter experiment says that it generates this many per gram, and a serving size, that little bag of Cheetos has 112 grams in it. I can multiply those two numbers together to get the number of calories in the little bag of Cheetos. And so that's where this technique comes in the most often. That's where it's most often used. And it's taking this paradigm, this juxtaposition of what happens in the water is the opposite of what happens in the reaction. The water is part of the surroundings. So whatever we measure happening in the water is the exact opposite of what happened in the reaction. The water got hot because it gained energy. That must mean that the reaction lost energy, gave energy away. The water gets cool because it's losing energy. Well, that must mean that the reaction has gained energy in some way. It's pulled energy from the surroundings. All right. Any last questions here about heat and reactions?